Good morning, everybody. Our speaker for today is Britta Horja, who will talk about toric geometry, conceptual combinatorics, volumes of standardized arrays.
Okay, I want to thank you for the opportunity to speak at this combinatorics conference. So, what I want to talk about today are some constructions that show up in toric geometry, and by now they're considered classical in the field, and of course they do have a combinatorics flavor, and so everything what I will say, in a way, at least from the combinatorics point of view, has is related to what we've seen so far. For example, the Stanley-Reisner ring idea, which is being ubiquitous in all the talks so far, and as probably many of you know, there's this idea. It's also used in the toric geometry and in general in break geometry. So what I thought about what should I say at the combinatorics conference, and what I decided is I want to sort of emphasize some points of view, some constructions that at least seem to me that are not that, it seems to me they're not that popular, or not popular, but not that used, at least in combinatorics. And so if, you know, if this, if some of these ideas look interesting to some of you combinatorialists, that will be interesting for me to talk about, or to see if this has different meaning and from your point of view. So, so let me start. So just to discuss a bit, to kind of, as a way of introduction, I want to start with an example, and this will be kind of the running example for this talk, maybe up to the end. So what I should mention is, what I'm going to say are ideas lifted from papers with Lev Borisov, older work with Lev Borisov, more recent work with Ludmil Khatarkov, and most of them are published, some of them are not published. So for various reasons, at least some of these results of Ludmil are not published. So what I want to start with, as I said, the example. So I want to start with a version of the two-dimensional projective space. So by the way, just to make our life easier, since this it is sometimes this is a relevant observation, but for me, K, the ground field, is always going to be C here. So what is this weighted projective space? So pardon but you'll see why the weights are chosen in a weird way. So this is an action of C star on C3. And of course, this is, everybody knows about this, as in the case of the usual projective space. To make sense of this in algebraic geometry, you kind of remove the bad locus. X1, X2, X3, 4. So in this, this is an idea that appears in toric, is the basic idea of toric geometry of constructing toric varieties. You have a group action, like maybe higher dimensional group action, but in any case, it's a torus action, and you want to understand the quotient. And you remove the bad locus, so you can do you take what's called a good quotient, the GAD quotient, and you work it further. So to capture this in toric geometry, and this again, I think this actually appeared already here, but maybe not exactly in this manner. So one way to capture it, of course, you can do it to capture these weights. You can think about this as some map from Z3 to Z, and such that weights, the matrix of this map consists exactly of these weights 2, 1, 1. And then the game you play is how do you encode this sort of in the more classical way that we've seen so far here when we talk about a fan, right? And where does the fan come in here? Well, if you want to understand the fan, what you do, you kind of take the kernel of this map, and one choice, of course, there is not a unique choice, like B, is here 1, 0, 0, 1, minus 2, minus 1. I hope, right? And so this is kind of where the fan story lives, that, as I said, we've seen already in a couple of the talks here. So the fan, you read off the vectors as the rows of this matrix, and they turn out to be 1, 0, 0, 1. So let's call this B1, 1, 0, B2, 0, 1, and V3, minus 2, minus 1. So this is the fan that is probably many of you are familiar, at least in the projective space, in the normal regular projective space. For this weighted projective space is singular, so it has a singularity, Z2 singularity, because this weights 2 there. And when I talk about fans, this is the simplicial complex, by the way. And so what I don't want to do, of course, I don't want to teach a course in toric geometry, but just to see how, you see here, if you, the map that I wrote induces a map. How do you see these group action? So this is a C star. And this map exactly gives you the action. So this acts on C3. So that's kind of the, yes.
Is there a star in this?
Oh, yes, thank you. And now, so talking about Stanley rights and ideal, we've already seen this. So I'm not sure about the notation, but in this case, is if I assign an xi for each vector, x1, x2, x3, is going to be x1, x2, x3, and then the next step in Horja geometry, and this is something that appeared, I'm not sure before, but certainly in the talk by Paul Bressler is, one way to what you want to compute is the cohomology of the Horja varieties, and certainly that plays a crucial role. And and I'll call this I'll put them So what you in this case is going to be plus some ideal J of linear relations, which sort of are basically as a variety, they're just translations of the algebraic linear relations on the variety in this for the homology classes, and J is generated as so now I will need to introduce some notation here. So this, by the way, this is the lattice M, and the dual of M. Oh, sorry, no, this is yeah, sorry, yes, and the dual of M is the lattice N. That's a traditional notation, and this linear ideal is, and for reasons that again I don't want to discuss further, I'm going to write here this as I mentioned, these are linear relations on the divisor classes corresponding to the vectors. So there is this natural picture where you assign each vector determines an invertible sheaf, the divisor in particular, and those are, and in this case, I guess, in general, in this case, I guess it's going to be from I equal 1, 2, 3. So for our situation, J is going to be x1 minus 2x3 and x2 minus x3. And if you work this out, what you come up with is k of x quotient by x cubed. That's an isomorphism. So no surprises here. This is very similar to the usual projective space. However, there is something that, and this I think showed up definitely in Karim's talk at some point, and and maybe Vasili's talk too. You want to subdivide the fans, and in algebraic geometry, this corresponds to blobs, right? So in particular here, there is a natural one to consider, and that is add a V4 minus 1, 0. So minus 1, 0 is corresponds to a blow-up, and what's special about this in this example is that see, when I do this, I got destroyed my micro. So when I'm still on the microphone, yeah. I think it's okay, right? Yeah. Okay. So when I do that, actually, I do not change the polygon. So, and from the algebraic geometry point of view, this is the birational transformation associated with this to the variety is what's called the prevalent birational resolution. So from birational point of view, also from, since these are examples that physicists use in string theory, we would like to see this Newberg variety equivalent to the old one for all intents and purposes, homology, categorical point of view, many points of view. So if we, so this, by the way, the new variety is actually is called F2, is the fifth root surface. And it's going to be it's smooth. So this, everything, it's in Bressler's language, this fits in his discussions, unimodular, simplicial. Of course, the previous one was simplicial too. So, so what we have here is that it's going to be so the irrelevant ideal, so-called, is going to be x1, x4, x2, x3 plus, and the linear ideal, one way to write it is x1 minus x4 minus 2x3 and x2 minus x3. Okay, I worked this out on the spot here. So anyway, so if you work this out, you come up with I think I'm trying to keep the x to be so x4 squared plus 2x x4. And the relevant thing for us is as a vector space A over C, the rank of this. Is 4. So let's find out K, I guess 1, X, X4, and maybe X4 squared. As opposed to the previous case when the rank here was written. So there is obviously a discrepancy for this for a subdivision, which, as I said, for all intents and purposes, should not change the theory, the fundamental theory of the underlying Fourier variety. And basically the talk is about how do we fix this? So what's, first of all, which one is the right one, right? That's a natural question. Well, you ask me, the polytope, the interior polytope of this fan actually has volume, well, normalized, of course, volume 4, right? Because I have here 1, 1, 1, 1. So it seems that this 4 is the right one. And so what's the fix? That's where and surprisingly, this, of course, the real fix is not such an old story. I mean, you know, Borg varieties have been around for a long time. So this is some probably 25-year-old story. And it has to do, of course, with the fact that we have, surprisingly enough, the problem became sort of prominent in algebraic geometry because of the physicists. So there is something that Baffa and Witten did, where they were concerned exactly with orbifolds like this, and the numbers they were getting were sort of will not agree with the algebraic numbers associated with the orbital, will not agree with algebraic numbers that you would get. And this is one example. As I said, here the dimension is 3, here the dimension is 4. So, as I said, I was trying to so we're trying to fix it. So we want to define a, well, I know I don't have a good name for this. I'll just, you may feel unhappy about this, but let's call it a generalized standard Weissman grid, which will fix this. Can be defined also for this situation, this singularities. For any simplicial fan, which again is something that we've seen here. So now in terms of notation, n lives in Z K maybe. Sorry, no, and it is ZK. And I have a fan. These are the rays, as I said, we've seen. And what I'm going to do, I'm going to define this. This is the semigroup. It's kind of a formal construction, semigroup generated by, or group ring, depending how to, I guess the group ring generated, so group ring generated by element that's just formally, I'm going to write x to n for all n. So what does this mean, by the way, just so that it's clear? I'm taking the fan, so this means when I write something like this, that means it's an integral point in the union of all the cones of the fan. So in particular here, for these two examples, there will be no difference in these in this group ring. Also, I'm taking all the points. If the total support of the fan is a cone, that's why we need this restriction. I only take, as I said, points that integral points that are in the cone. So and I'm going to add here that I'm going to deform the product, namely x and 1 times xn2 is equal to xn1 plus n2 if n1 and n2 in the same cone of sigma, 0 otherwise. So then the definition that I mentioned already is that, well, I mentioned the fact that we want a good definition that works, is that I'm defining this generalized Stanley-Rice ring as the quotient by the ideal generated by, I know how to call, usually, people call them Z1, Z, where my lattice is ZK. Well, ZI's are exactly these elements I was writing earlier. So M, VI, X, for all n. Of course, it is enough to make a choice of a basis in n. By the way, since we've seen this already, it turns out that in this context, this is going to be a regular sequence, and we're talking about Combinatorial rings, and so let's try to understand. And I'm claiming that this is the right notion. So let's do one for so going back to our example. You see, if we look at the generalized Stanley-Rice ring associated, sorry, so I'm talking about the black vector, so just the weighted projective space. What you get well, you'll get certainly this but there will be an extra component, and I'll tell you where it comes from. It comes from exactly from this extra sum, comes from exactly from this point. Because you see that point in the same group ring, this point, x v to the v4 you want, is not generated by anything else, obviously. Right? So I cannot generate it. It's true that x to the v4 squared is written as xv2, xv2, x or x2, let's say x3. So so we get the right dimension as so the general proposition, that's why I said volumes, is that the rank of this is in the appropriate sense with the appropriate normalization is always equal to the volume of P. So basically now I should say some words here. So this is this type of decomposition is something that happens in general. So for any toric variety defined by a simplicial fan, there will be the Stanley-Rice ring will break up into sort of the classical homology plus a bunch of extra sums, and the exact name for those in topology, they're called the twisted sectors. So what this in for those of you might have seen this. So, in good cases, so not all cases are good. This homology is what's called orbifold or Chen-Luan homology associated to the orbifold, the toric orbifold. And what this, what the meaning of this in general is not clear. So it certainly makes combinatorial sense here. I haven't done anything illegal combinatorially, but depending on the configuration, sometimes the geometric meaning is missing. And as I said, this is something that people have thought for a long time. It's Chen-Luan, about, as I already mentioned, about 25 years. So, are there any questions? Yeah.
That's really good. But what was it that made this -1 so natural? Is it that visually point on convex flow or?
And two things. First of all, it refines the initial fan into a fan with all, which is now unimodular. So all the big cones are generated by basis, right? Number one, and number two, what was special about it is that the vector actually ends up on the boundary of the polygon. But geometrically, if that doesn't happen, that we change the canonical class and the volume will change.
This vector rank is the volume. This is kind of like a combinatorial relation in this way.
Yes, but there are toric examples in higher dimension where you cannot break it into you cannot do unimodular subdivisions. So then yeah, it's just really the model. It has a tremendous meaning. I want to say a few more things about this. But again, for me, the fact that there is here some kind of, combinatorial object, a regular sequence, it's very similar to what we've seen so far. And as far as I can tell, I haven't seen this at least I haven't seen it used in combinatorials. So in a way, it looks to be, as I said, as these invariance properties that are missing in the classical case. And now I want to give a different presentation of this ring, which again is something that perhaps is not that familiar to combinatorialists, but that's why I'm giving it a try. So, so whenever you talk about homology, and especially when you have a notion which you don't know how to look at, another sort of idea that again is also showed up in although it was briefly mentioned in Paul Breslau's talk, you look at the Grothendieck ring, and maybe I should say this. So what are there is a combinatorial way of indexing these twisted sections. So what's special about this? Oh, I erased the, unfortunately, let me draw it here. So what's special about this point is that if you build what's called the box of the fan, so you take the Minkowski sums of all the vectors with coefficients less than with coefficients less between 0 and 1. Well, so you do this for each large cone, you get these boxes, and the components here are going to be in one correspondence to the elements that you get in the boxes. So in particular here, we have this that corresponds to this component. And then, as I said, there is an extra point there, which corresponds to this. And that's the general story. So it's always going to be that you look at this box of the fan, and each element of the box corresponds to one summon in this standardizing homology. Okay, so this is a very general notion, has nothing to do with, and it shows up also in combinatorial, you can do it for many objects in mathematics. So for us, if I have an x, let's say just storing variety, or they're not really varieties, but they're orbitals, rather, storing variety orbital. Or stack, that's a word. Trying to avoid. So this is the free abelian group generated by symbols of the type, at least for us, this is going to be enough to take vector bundles. Next, with one relationship, namely that V1 minus V2 plus V3 is 0 if there is a sequence, an short exact sequence. So again, this is, I'm sure you may have seen this notion in other contexts. You can define even for polytopes. There is something like a Herculean ring, and maybe sometimes you have to wiggle the relationship. But in algebraic geometry, at least, this is kind of the notion that works well. It turns out there is even a product on this, so that's why it's sort of tensor product has to be a little bit, in general, you will have to kind of take a derived version of the tensor product, so allow for some X groups, but you can just think about it for now as a tensor product of bundles. So it turns out that for this type of Horja variety, which is an orbital, so in other words, defined by a simplicial fan, there is a description which is also a Stanley-Rice type description of this Grothendieck ring, which in a way it's easier than that. I don't know if it's easier, but it's kind of also very natural. So the K0, and this is the result that's obtained a long time ago with the Borisov. So it's so you see again the vectors play a crucial role. So to each vector you can assign a line bundle. It's called Ri. And being a line bundle, you can invert it. So these are going to be actually invertible sheets. So you can talk about Ri to the -1. And the relationships are very similar to, as I said, the Stanley-Rice one. So there is the one that we expect, except that it's a little. So if I consists, or if I is a subset of 1 to n, such that the vi I do not form a cone, sigma, and another bunch of relationships, which, it's a product, this is really a translation of the linear relations in the Stanley Reisner ring case. So part two, again, this goes, part two of this goes back to what actually Bresco was hiding from us in a way there. Because there is an amorphous, which is kind of a churn, I'll put in quotes, churn factor, which lands into and gives an isomorphous, but not the ring isomorphous, but only a vector space isomorphous. So let me just to see that this is not that scary. Let me go back to the projective space, weighted projective space case. While we're doing more time. So if we go back to this example, so D1, 1, 0, D2, 0, 1, D3, minus 2, minus 1, then the linear relationships are R1 times R3 to the negative 2 is 1, and R2, R3 to the negative 1 is 1. And Stanley Reisner relation is that 1 minus R1, 1 minus R2, 1 minus R3 equals 0. So what you see is that if Ri, well, K0 comes out as if we choose, if we keep R3, say, as a kind of naturally keep R3, so 3, R3 plus minus 1. And here R1 is, so it's going to be 1 minus R3 squared, and times 1 minus R3 squared, because R3 is the same as R2. So I don't need to put 0 anymore. And again, as a vector space, this has rank 4, as you like this. And of course, there is this is Arcanian, in fact. You can localize the maximal ideals, and each localized component corresponds exactly to one of these Stanley Reisner components corresponding to a certain physics sector. And one more thing I want to say about this, there is even a deformed version of this. Maybe again, my reason for giving this talk, trying to present these constructions, which are kind of natural from the point of view of Horja geometry, maybe you find them interesting and useful in some contexts. So if you take a data you can take a deformation of this. And again, this is natural from the geometric context. It's kind of a deformed Britain's rings, where the only modification here is that we take here e to the 2 pi I guess means square root of -1 beta. And this also can be interpreted of some kind of Brutally group of deformed the deformed Brutally group, and what's what's interesting about it that in general for generic data, it is semi-simple. In other words, it's not going to look like this. So this one has a double root, for example. This polynomial that it's going to break up into simple roots, so to speak. That happens for generic, but then you have these wall crossings. The rank doesn't change, but you have wall crossings, and you get pictures like, of course, it's all up to integral translations. You'll get pictures like, I don't know, in the plane, something like that. So, and the very interesting stuff sometimes happens at these points when you choose beta to be 0, or sometimes you have another interesting point there. So again, and there is an interpretation of this. I'm not going to write it down because it's more technical. Of this the Stanley Reisner ring 2 with respect to this beta, which, by the way I came up with is in this context of Gables Zelevinsky machinery and trying to solve some partial differential equations that have a meaning in mirror symmetry. So, but again, they're just simple algebraic gadgets, and it's kind of interesting that, as I said, as you move, you have these wall crossings and the ring changes. So again, I do not know the meaning of these wall crossings, although I thought about it. So. Okay, so I want to, I have about 10 minutes. I want to finish off with another application of volumes. That I'll try to present from the combinatorial point of view. That, for me at least, that was kind of interesting exercise to look it up and see what people did. So, so I want to talk about the Lorentz construction. And in this context, Gale duality. And, well, I'm sure people might, this combinatorialism might be unhappy about what I call the Lorentz construction and what I call Gale duality, but it's not that far from what anyone would call the Lorentz construction. Let's say there is, I guess, the textbook by Ziegler, right, where it's sort of the reference book, so it's almost the same as what he calls the Lorentz construction. On the other hand, because I've seen lots of places where this is a little different. So, and what I should say, just to start with, this is in some work I did with Ludmil, where what we're trying to do is, for this case of toric writing, we're trying to construct what's called a categorical resolution of a toric array. So it's kind of a, in a way, an algebraic gadget that is a resolution across all these birational resolutions that you might have for a toric array. And as I said already, this is some idea that I guess is very natural in physics. For them, it's kind of, there's almost nothing to prove, but mathematically it's still challenging, and people are trying to work examples where this works, and that's what we're trying to do. So let me start, let me just present quickly what we came up with. I just want to bare bones facts here. So B, I'm going to start with, this is a list. It doesn't have to be a set. So it may have repetitions, in other words. Why is B not A? Don't ask me that, I forgot, but there is a reason. In a K, I think it was K dimensional lattice. But let me call it D. Sorry for that. My notes are with D here, so I don't know why. So we assume that that B1, Dn generate N as an abelian group. So what is this Lorentz construction? As I understand it, as I said. Not as I understand it, as what I call my Lorentz construction, which, as I said, is a little different from other people call. So it's basically you start with this list B, and you associate. Now this is going to be a set, LB I call it. So if this is B1 Bn, this gets transformed into B1 plus E1, Bn plus En, E1, En. So this lives inside N plus Z to the N, which is of course a Z D plus N. And there are many reasons for doing this. It somehow seems to me combinatorially that if you want to do these stellar transformations, and which geometrically they're birational transformations, when you limit things to the Lorentz construction, it's easier to see them, so to speak. And it's something that, of course, it shows up in oriented matrix theory. Books about it. Not an expert in it. So this LB, so the remark LB consists, so this is one big advantage of this Lorentz transformation of all the vertices of its convex hull. So no surprises here, combinatorially. And then the other thing to see is that if you take a map, something like that, say sends each AI in 1 and each VI in 0, then you see that H of LB is equal to 1. So all the vectors, so in other words, the set is contained in the hyperplane, which is another good thing from the toric geometry point of view, because the singularity associated to this is more manageable. So let me give you one quick example in the 1 minute. Then I think I can write again the combinatorial class, or maybe not yet. But let me do one example. So if my list is V1 equals V2 equals 1 in Z, so this is B, LB is going to be 1, 1, 0, 1, 0, 1, because this is V1 plus V1, V2 plus V2, and 0, 1, 0, 0, 0, 1. So if I call these, let's call them W1, W2, E1, E2, what do we see? We see that W1 plus E2 is equal to W2 plus E1. So in other words, what we're talking about here is the famous quadrilateral, which admits two triangulations, and it's also known as the IKEA flaw. Discovered by IKEA in the 50s, long before there was any Horja geometry or any combinatorial understanding of this. Okay, so where's the Gale duality? Well, I mean, I'm going to write down exactly the sequence that I already had. So this is going to be B plus N. B. Let's call this map A. So the way I understand Gale duality is a duality between these two objects. And again, this is some combinatorial gadget that people have used for a long time, lots of points of view, but just at the linear algebra, algebraic point of view, it's kind of, you think about these vectors that you start with determining some kind of hyperplanar region. On one side, that corresponds in the one-to-one correspondence with the relations on these normal vectors that are zero. The relations on these normal vectors, the kernel, if you want, of some matrix. And the dictionary is very nice and very useful. One thing about to keep in mind here is that this is not your sort of run-of-the-mill Gale duality, because here you can get torsion. In fact, if we really want to be honest here, then in general, we really want to produce an honest duality theory. We should also have torsion and maybe 2 more minutes. Yeah, torsion on the other side, and this is kind of. But we did this some time ago, never published it, and I think by now this has been done in combinatorials by I don't know if I have the name, by some Italian name guy. So so let me just say, as I said, what we wanted to produce here, there were some categorical resolutions, which I haven't said any word about, but the point of view is that the categorical resolutions are associated for a Lorentz variety, are associated with certain polytopes in P or here, depending what you want to think about, which are in fact zonotopes. So so the theorem that we prove, but again, were published is that the rank of this, which is, this is not the main theorem, but it's kind of the sort of the main requirement for this to work, in fact, is that the rank is given by the volume of the zonotope determined by AB1, ABN, or another way to say it is the volume determined by the zonotope associated to Vn. So, and I'll stop here. I just want to say a few words here. So when I talk about volumes of zonotope, one way to think about it, the way I like to think about it is, of course, there's a volume, but it's also an issue about, you can think about it as a counting problem of integral points. So in other words, this statement is about a statement about the number of lattice points inside this zone. By the way, I should say what the zonotope associated with one of the vectors consists of all the possible linear combinations of vectors with coefficients between 0 and 1. So, and so now if you have a polytope which may contain integral points, if I just jiggle it a bit, push it a little bit out, so it becomes generic, then its volume really counts with the appropriate normalization. It really counts number of integral points. So this is some duality, and something similar, I think, if I remember correctly, is discussed in one chapter of this book by De Concini and Porcesi, where they do talk about counting integral points. But again, this sort of, in a way, as I said, the Gill duality here can be viewed also as a duality about these volumes that sort of I started the discussion with. So in the appropriate, I'm cheating here because in the appropriate term, there is distortion that have to be accounted for, and there's some extra factors here, but essentially, that's what the result is. Okay, thank you.
Right.